This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, so this is then the final class in quantum mechanics. That's, of course, wrong. We will continue with some quantum mechanics when we get to quantum field theory, but the last of a sequence. And I think the most important, the most important two subjects that we can do in quantum mechanics to finish the subject up is the harmonic oscillator and angular momentum. Let's see if we can squeeze it into 2 hours. All right, so the harmonic oscillator is, of course, basically a particle. The mathematical structure of it is the particle moving on a line under the influence of a force, the force being the restoring force, the Hooke's law restoring force of a spring. That's the that's a physical example of a harmonic oscillator. There are many, many examples of harmonic oscillators in physics. In fact, really almost any system, if it has a stable equilibrium of some sort, and you disturb it a little bit, it will oscillate about the minimum, about the stable point. Examples are a weight hanging from a spring. Okay, so the ceiling, a spring, a weight. We assume, of course, not to assume, I think we can prove for the case of an ordinary spring that the weight, the mass, finds an equilibrium position. It finds an equilibrium position at the position in the gravitational field in the vertical place here, where the gravitational force down exactly balances the spring force up. The gravitational force is constant, doesn't depend on how high the mass is, the gravitational force, but the spring force varies from nothing when the spring is unstretched and gets bigger and bigger as the spring is stretched. And so at some point, an equilibrium is found between the spring force and the vertical downward force of gravity, and that's the equilibrium position. At that point, the mass can just sit at rest with no motion whatever. But then if we disturb it a little bit, it will oscillate back and forth, or up and down in this case, and execute harmonic oscillations. If we ignore friction, air resistance, and non-ideal behavior of the spring, it will execute genuine harmonic oscillations, meaning that it will vibrate back and forth with a sine pattern, sine and cosine pattern. That's the classical description of it. There are lots of other examples of harmonic oscillators. An example, a very important example in physics, is waves, wave motion. If you stand at a particular point and you watch a wave going past you, of course it oscillates up and down. It could be a water wave. Water waves are not ideal harmonic oscillators. They're a little more complicated. But nevertheless, if the wave is moving past you and you stand there and watch it, it just goes up and down the same way as this does. And so that's another example of a harmonic oscillator. Sound waves vibrating. Again, stand not watching with your eye, but listening with your ear. Again, a typical sound wave of a given frequency is again a harmonic oscillator. There's all kinds of harmonic oscillators in nature. The mathematics of them is all the same. So we choose to concentrate on one example, just the spring vibrating up and down, but the mathematics applies very, very widely. And in fact, the mathematics continues to apply widely when we go to quantum mechanics. So by quantizing the simple system, now, of course, no genuine spring with an ordinary mass attached to it has any reason, we would never have any reason to want to quantize it in practice. It's too heavy for quantum mechanics to matter. Quantum mechanics does describe it, but for ordinary heavy masses and typical spring constants that you would encounter if we went into the laboratory here and got a spring out, quantum mechanics would be completely unimportant, or the corrections of quantum mechanics to classical mechanics would be completely unimportant. But nevertheless, it's worth taking this as an example, subjecting it to the rules of quantum mechanics, and then it really does apply to all sorts of very much lighter systems, not a heavy kilogram mass hanging from an ordinary spring, but for example, molecular motions. Molecules have equilibrium positions. The atoms have equilibrium positions. If you disturb the atoms a little bit, they vibrate about the equilibrium positions. And again, they describe harmonic oscillators. For those things, quantum mechanics is important. So we take this as a model and subject the physics of it to quantum mechanics. All right, let's begin with the Hamiltonian describing the mass on a spring. Well, in fact, let's begin with the Lagrangian. It's a good place to start. The Lagrangian is 1/2 the mass times the velocity squared. And let's call the displacement from the equilibrium position, let's call it x. Even though on this picture here, it's sort of the y coordinate, let's call it x. And x dot is the time derivative of x, that's the velocity squared. That's the kinetic energy. Now, it is always possible to absorb into the definition of x the mass. I will do so just to make a sort of standard oscillator where the mass is equal to 1. I can always do that even if the mass is not equal to 1. All I have to do is define a new coordinate. For the moment, let's go over here and call it y. Take y to be equal to the square root of m times x. What is y squared? Y dot squared? Y dot squared is equal to m times x dot squared. So if I chose to work with the y coordinate instead of the x coordinate, it's really just a change of units. If I decide to change units from y to x, or from x to y, then y dot squared is equal to m x dot squared, and I could call this just 1/2 y dot squared, and get rid of the mass altogether. Let's do it. It will simplify many of our equations. Okay. Good. Now that I have exhibited how to do it in terms of a new variable called y, let's just call the appropriate variable x. All I have to do is get rid of the mass here, and remember that the new x coordinate is just the old x coordinate times the square root of m. Good. So we get rid of the mass in that way. The mass plays no special role. The important quantity is the spring constant, but again, I'm going for our purposes to set the spring constant for the moment. Let's see, shall I call the spring constant 1? No, let's not call the spring constant 1. I'm going to call the spring constant omega squared. All right, so the spring constant, how does the, this is Lagrangian, not the energy, the Lagrangian, this is L, minus, this is the kinetic energy, minus the potential energy. What is the potential energy when you displace an oscillator away from its equilibrium position? Well, it increases if you displace it one way, the energy. It increases if you displace it the other way. In either direction that you displace it, the potential energy increases. That's why it tends to come back to the origin. And so the natural expression is proportional to the square of the displacement. If the potential energy was just proportional to the displacement itself, it would increase in one direction, it would increase in the positive in one direction, increase in the negative in the other direction. That's not what we want. We want something which increases in both directions when we displace this object. And the natural thing to write down is something proportional to x squared. The coefficient in front of x squared is, we can name it anything we want, but the standard name is to put a factor of 1/2 there, and then the spring constant k, but I'm going to call the spring constant omega squared. Omega is, in fact, the frequency of the oscillator. This is the Lagrangian. Let's just very, very quickly work out the equations of motion. Remember what we do? We take the partial derivative, or the derivative of the Lagrangian, partial derivative of the Lagrangian, with respect to x dot. That has a name. It's the canonical momentum conjugate to x. We take partial of L with respect to x dot. That is just equal to x dot in this case. No mass, because I've set the mass equal to 1. Right? And then we time differentiate that. That gives us x double dot. And we set that equal to the partial derivative of L with respect to x. Do I have that right, or do I have the sign wrong? I think I have the sign right. That's partial derivative of L with respect to x. And what is that? That's omega squared. That's minus omega squared x. Well, this is just F equals ma. Mass is set equal to 1. Here's the acceleration. And it's equal to minus the thing that I've called omega squared times x. What is the minus sign doing there? Why is it minus? Anybody know? It's a restoring force. That means if you increase x in one direction, the force will pull you back, and that's what the minus sign is there. Okay, so that's the equation of motion. X double dot equals minus omega squared x. And the solutions to the equations of motion are sines and cosines. The solution of this kind of equation is just x is equal to a times cosine omega t, same omega, plus b times sine omega t. That's the general solution of the harmonic oscillator, sines and cosines. And this frequency here is just this omega. The point is, when you differentiate twice, you pull out a factor of omega squared. Okay? So that's the classical harmonic oscillator. All right, to go to the quantum harmonic oscillator, the first thing we want to do is, well, we have several steps that we have to do. We first have to construct a space of states. A space of states. And the space of states, or a vector space describing the states of the system, the vector space for a particle moving on a line is just the functions of x. Psi of x, which is the amplitude to find the particle at position x, defined in such a way that psi star of x times psi of x is the probability density to find the particle located at a position x. The probability density, the probability per unit interval. This is the probability density, P of x. And the space of states, or the vector space describing the quantum mechanics, is just the vector space of the functions psi. All right, that's the first step. We now have a sort of kinematics. We now have a specification of what the states of the system are. Next step is to find a Hamiltonian. If we want to know how, for example, two questions we might ask. How does the state vector change as a function of time? To know that, we have to know the Hamiltonian. Or, not or, but another question we might ask is, what is the energy levels? What are the possible energies of the harmonic oscillator? And the possible energies of the harmonic oscillator are also determined by the Hamiltonian. So to get started with anything useful, we have to have a Hamiltonian. For that, we go back to the classical, good, just close it. For that, we have to go back to the Lagrangian and apply the standard rules to the Lagrangian to find the Hamiltonian. I'll just remind you what they are. The Hamiltonian is just equal. Well, before you do that, you have to define the canonical momentum conjugate to x. That's just p, and canonical momentum is partial derivative of L with respect to x dot. That's just x dot in this case. Very simple. P is equal to x dot. Okay, the Hamiltonian is px dot. This is classical mechanics now. Classical mechanics, which was which? 2 quarters ago? Am I right? 2 quarters ago. Px dot minus L. Okay, Px dot minus L, let me short circuit it. The Hamiltonian is the energy, and it's always given by the kinetic energy plus the potential energy. The Lagrangian has minus the kinetic energy, minus the potential energy. The Hamiltonian has plus. The Hamiltonian is just 1/2 mv squared kinetic energy, which in our case is just x dot squared, plus the potential energy. Plus the potential energy now means plus 1/2 omega x squared, omega squared x squared. Okay, that's the energy, but this has been expressed in terms of velocities. The things which we know how to turn into quantum mechanical operators are the canonical momentum. Canonical momentum has a standard interpretation as an operator in quantum mechanics. So let's re-express the Hamiltonian in terms of canonical momenta. That's easy. X dot is equal to P. So the Hamiltonian is just 1/2 P squared plus 1/2 omega squared x squared. And that's it. That's the Hamiltonian, the classical Hamiltonian. And how do we make quantum mechanics out of it? We make quantum mechanics out of it just by understanding x as an operator. X is an observable, the position of the oscillator, and p is an observable. Both of them can be defined through their action on psi of x. They're Hermitian operators, and their action on the state vectors of the system are straightforward. Okay, we know what they are. X just multiplies the wave function by x. I don't know how to write this except to write that x acts on psi of x to give x times psi of x. That's a stupid looking equation, isn't it? Oh, I know what to do. Let's call this, put a hat over it to indicate that it's an operator, and let's put a ket vector around this to indicate that it's a ket. And then we shouldn't write equals, we should write that this corresponds to multiplying psi of x just by x. It takes every wave function and creates a new wave function out of it. X multiplication by x is, yeah.
Isn't it equal if you make a cat out of the other one?
Yeah, but then I'll have to make an operator out of this. So I'll just write the same thing over again. Right. The rule is every time you see x, think of it as multiplication on the wave function by x. It's an operator, and it operates on the vectors which are functions of x. All right, what about p? P, of course, p on psi corresponds to minus I d by dx. Now, there's a factor of h bar, isn't there? I'm going to put the h bars in at the end. Let's set h bar equal to 1. In the end, we can figure out where the h bars go by dimensional analysis. All right, so p on psi is just minus I d by dx on psi of x. And now we can figure out what the action of the Hamiltonian is on a wave function. You simply multiply p by itself and act on the wave function. What does that mean, p by itself? It just means that you act once with p, and then you act again with p. So let's figure out what that is. Let's write h on psi corresponds to 1/2. Now, let's first apply p once. That's minus I d by dx psi of x. But that's only operating with p once. We want to hit it again with p. So we just have to multiply it again, not multiply it, but differentiate again, another factor of minus I d by dx. Okay, so we can write it minus I d by dx acting on minus I d by dx psi of x. And what is that? That's the second derivative of psi with respect to x. Minus I times minus I gives us a minus sign. Minus I times minus I is the same as plus I times plus I, which is altogether minus 1. Did you get that? Okay. So this is minus d second psi by dx squared. Minus 1/2 d second psi by dx squared. Incidentally, why am I writing partial derivatives here? I'm writing partial derivatives because psi in general also depends on another variable. The other variable being time. Right. So psi in general will depend on time. Time is not an operator. Time doesn't have the same status as x. It just says the state vector changes with time. Okay, so the partial derivative indicates at a fixed time. All right? That's 1/2 d second psi by dx squared. Yeah, thank you. Negative sign. Right, that's the first term, that's the p squared. And then the second term is just plus 1/2 omega squared x squared times psi of x. Right. That's the action of the Hamiltonian on psi. But what is the Hamiltonian for? The purpose of the Hamiltonian, two purposes for the Hamiltonian. One of them is to tell you how the vector changes with time. So let's write out the Schrodinger equation. The Schrodinger equation is I d psi by dt is equal to h psi. That's essentially the definition of the Hamiltonian. Do I have the sign right? I always forget. Minus I d by dx is momentum, so plus I d by dt. Yeah, there's a sign difference between momentum. Yeah, that's right. I d psi by dt is equal to h psi. And now we can substitute this. We can substitute this, and let's do so. Minus 1/2 d second psi by dx squared.
Is that a partial t on the left, or is it a?
This?
Yeah.
Well, that's a partial derivative because it means you keep x fixed. All right, you keep x fixed. This is the derivative of psi of x with respect to t, but at fixed x. Okay, good. This is the derivative of psi with respect to x at fixed t. Okay, so that's the first term, and the second term is plus 1/2 omega squared x squared times psi of x. Okay, that's the Schrodinger equation, and what it tells you is if you're given psi, for example, I give you psi at some particular time, the real and imaginary part, notice that the real and imaginary part, notice that the equation is complex. It has an I in it. Now that means even if psi was real at the starting point. Let's imagine that psi was a real function at time t equals 0. It will very shortly develop an imaginary part. Okay? So the wave function, when it varies with time, it's not consistent to look for a real solution. The solutions must be complex, because even if it started real, it would soon become complex because of this I here. So psi is a complex function of x and t, and it satisfies this equation. This tells you how it changes. If at some instant of time, now I'm imagining that this is both the real, it's a cartoon of a complex function, psi of x at an instant, at time t equals 0. This tells you how it changes with time. All right, this is the dynamics. This tells you how things change with time, it tells you how things evolve. And you could solve it in a number of ways. One way of solving it would just be to put it on a computer. Start with psi, update it a little bit by calculating the derivative. Once you calculate the derivative, you find out how it changes in a small increment of time. Once you know how it changes in a small increment of time, you add the incremental change to psi, and you keep doing it over and over and over again, and whatever psi is, it will do some interesting things. It'll move around somehow. In fact, it will move around very much like a harmonic oscillator, back and forth, back and forth, back and forth, but that's not completely obvious at the moment. The other thing you can do with it is to calculate the energy levels, to calculate the energy eigenvectors and the energy eigenvalues. It turns out, and we'll go through this, I think, that when you know the energies and energy eigenvectors and eigenvalues, you can work out the time dependence without doing any differential equation. That's because you know the time dependence of each energy eigenvector, but we'll come back to that. Okay. So let's concentrate on the energy eigenvectors, themselves. How do we find them? We write down the condition for an eigenvector. Right? The condition for an eigenvector is that h times, let's call it psi sub e, e for energy. A particular energy level indicated by the value E here, h on psi of E equals E times psi of E. Or psi sub E, I guess. Psi sub E. The sub E, as I said here, just indicates which particular eigenvalue. Now, this equation does two things. It solves or it doesn't solve, but it defines an equation for the wave function psi e of x. It gives you an equation for that, but it also tells you what the possible energies are. I'll show you why in a minute. I'll show you why it picks out a certain subset of values of E as possible energy levels. Okay, but let's write this equation now in terms of psi of x, not as an abstract equation, but as an actual equation for psi. All right, what is h? H is, it's the right-hand side of the Schrodinger equation up there, minus 1/2 d second psi by dx squared. This is h on psi, or the representation of it in terms of ordinary functions, psi of x, plus 1/2 omega squared x squared psi of x equals E times psi of x. Looking for solutions of that equation, which means both finding the values of E which permit a solution and also then solving the equation, tells you what the eigenvectors and the eigenvalues of the energy are. Okay. Now, first of all, why would it be that, that not every value of E is a possible energy eigenvalue? You can solve this equation for any value of psi of E. Okay? But let's see, shall we? Yeah. All right, I will tell you what happens when you start looking for solutions. If you start solving this equation, you will find out that when you solve it for energy E, when you solve for psi of x, you essentially find two solutions. Anybody know why you find two solutions for an equation like this? Because it's second order, because it's a second order differential equation. It has second derivatives in it. And whenever you have a second order differential equation, it requires two pieces of information to get a solution started. And so there are two independent solutions of an equation like this. Each solution, we'll see, is exponential in a certain way. It varies. One solution goes like e to the some constant times x squared, excuse me, and the other one goes as e to the same constant times minus x squared. There are two kinds of solutions, ones which blow up and ones which fall to zero. So for example, imagine starting, this is a second order differential equation. You can start at any value of x, and you can start building yourself a solution by simply numerically, for example, building a solution. You know psi of x. You can postulate a value for the derivative of psi of x and start iterating your way to a solution of this second order differential equation. Generally speaking, if you pick an arbitrary value of the energy of E, what will happen is you will find both kinds of solutions are there. To find the solution, you will have to superpose the two of them in general. And in particular, one of the components of the solution will be exponentially increasing. Exponentially increasing out at infinity. That's a terrible thing. It means that all of the probability is way, way out at infinite distance. In other words, the probability density is exponentially increasing. The relative probability of being anywheres relative to being very far away is zero. Now, that's not a good thing because the energy contains x squared. If the probability is overwhelmingly very far away, it has to mean that the energy is huge because of this x squared term. And it would be. So there's something wrong with these exponentially increasing solutions. The right way to say it is the true space of states is the space of states of square integrable functions, of functions which are square integrable. Namely, they have the property that psi star psi dx is equal to 1, total probability equal to 1. That precludes functions which exponentially blow up far away. They would not be square integrable. So the trick is to look for values of E which allow solutions in which the exponentially increasing part is absent. There are certain discrete values of the energy where the exponentially increasing part just isn't there. In other words, if you start at some point and you start iterating your way to a solution in both directions, that's the key, that in both, it's not hard to find wave functions which decrease in one direction or the other direction, but typically you get into a bind. If you look for solutions which decrease in one direction, you'll find they blow up in the other direction, and vice versa. Only at very select values of the energies are there solutions which decrease in both directions. Those select values are the energy eigenvalues of the harmonic oscillator. So let's see what we can do. Let's see if we can figure out what they are. Yeah, there's another intuition. Let me give you another intuition also that helps you understand the harmonic oscillator. It's the uncertainty principle. The uncertainty principle between x and p. Classically, how do I minimize the energy? I force both, but remember, the energy is positive definite, or positive. P squared and x squared are both positive. Classically, it's quite clear how to minimize the energy. You set p and x equal to 0. But quantum mechanically, that's too much. There's an uncertainty principle. There's an uncertainty principle which says that you can't set both x and p equal to 0. You can try to find some compromise where x is not too spread out and p is not too spread out, but you're not going to ever find a solution where both, or a quantum mechanical wave function where both x and p are both equal to 0. And so you have to find some compromise. Because you had to compromise, it means that the ground state energy, the lowest possible energy of the system, will not be 0. Both p squared and x squared, neither will be 0 because of the uncertainty principle. So one of the things you should expect is, first of all, that there are no negative energy levels. How can there be negative energy levels when when both of these are positive? They're both positive operators. Thought of as operators, they're both only positive eigenvalues. P squared and x squared are positive. So there are no negative energy levels. And in fact, there is not an energy level with 0 energy. The first energy level has some positive energy. All right, I'm going to tell you what the first energy, the lowest energy level is. And by showing you a solution of this equation, and maybe if I can figure out how to do it while we're here, I'll see if we can prove that there isn't a lower energy level. But let me show you one solution of this equation. It's not with E equals 0, as I said. There are no solutions with E equals 0 because of the uncertainty principle. Okay, let me show you a solution. There's a solution which looks like e to the minus, I think it's omega, or I can't remember if it's omega or omega over 2, x squared. That's an interesting wave function. It's concentrated near the origin. So it does correspond to an oscillator which is more or less concentrated near the origin. Let's see if we can figure out what the Hamiltonian does to it. Let's calculate what the Hamiltonian does to it. The first term, the minus 1/2 d by dx squared. Let's first take that. All right, let's differentiate it twice with respect to x. That's the first term in the Hamiltonian here. This is psi. Let's differentiate it once with respect to x. To differentiate it with respect to x, I have a feeling there's a 2 here. Let's try it with a 2. I can't remember. Let's put a 2 in. If the 2 isn't there, we'll find it out, and I'll get rid of the 2. What happens if I differentiate e to the minus omega over 2 x squared once with respect to x? Anybody want to try for it? Let's see. It will certainly give us outside a minus omega over 2, right? Then when you differentiate an exponential with respect to an argument, you just get the exponential back, e to the minus omega over 2 x squared. But then you...
X squared. And you're going to get x twice.
X once. First derivative.
Oh, first derivative, yeah.
First derivative, yeah. And that will give you a 2x. From differentiating x squared, that will give you a 2x. Okay, well, it looks good. The 2's are canceling. That's a comforting thing. I'm not sure why I'm glad they're canceling, but let's rejoice. I think, is that it? Do I have it right? That's the first derivative. That's dψ by dx. I hope. Now, what happens if we differentiate it again? If we differentiate it again, we get two contributions. One, we're differentiating a product. All right? We're differentiating a product. The first term comes when we differentiate the first factor in the product. Okay? This is dψ by dx. If I differentiate it again, I get two terms. One of them just comes from differentiating that. That's minus omega e to the minus omega over 2x squared. The derivative of omega x is just omega. Okay? What happens if I differentiate the other factor? The other factor will give me minus omega x, and then the derivative of this with respect to x. But we've already figured out what the derivative of this with respect to x is. It's just multiplication by minus omega x. So that gives us, I think, plus omega squared x squared times e to the minus omega over 2 x squared. That's it. That's the second derivative with respect to x squared. Okay, so that's the first factor. Next, plus 1/2. I have a feeling I'm going to be sorry that I threw away that 1/2. Yeah, it does look like I wanted to, well, we'll figure it out. Okay, then there's plus 1/2 omega squared x squared. Do I have the sign wrong? I wanted an overall minus sign. Yeah, I think I have the overall sign wrong. I want minus 1/2 of the second derivative. Okay? Ah. The sign is right? Let's see. When I differentiated once, it gave me a minus sign. Yeah. Okay.
The thing on the left-hand side that you've got there is
Yeah.
just the second derivative?
Yeah, it's just the second derivative.
So you still have a minus 1/2 to multiply.
Right, right. Oh, good. We still have minus 1/2. Good. So let's put in the minus 1/2. All right, so that will give us a plus, am I right? I don't want to disturb it unless I know what I'm doing. I think I should write this being plus 1/2. Good, so this should be plus 1/2. And this one should be minus 1/2, right? That's the minus 1/2 in front of the d second psi by dx squared. Then there's plus omega squared x squared. So that's plus omega squared x squared times psi. Psi is e to the minus omega over 2x squared. And that we would like to be e times psi. That we would like to be e times e to the minus omega over 2x squared. Okay, let's examine the terms. There are two kinds of terms. One of them has x squared e to the minus omega over 2x squared. In other words, one of them has an x squared sitting out in front. In fact, there are two of them. These two both have omega squared x squared over 2 multiplying the wave function. But fortunately, they cancel, because there would be nothing to cancel them against in the rest of the equation, minus and plus. So quite independently of what the eigenvalue is over here, these two cancel. We don't have to worry about them. They're gone. What's left? What's left is 1/2 omega e to the minus omega squared x squared equals e times e to the minus omega over 2x squared. In other words, a certain constant times the exponential is equal to another constant times the exponential. Well, it's quite clear how to solve this. You just set e equal to 1/2 omega. E equals 1/2 omega. That will solve the equation. So we found one eigenvector of the Hamiltonian with eigenvalue. Let's summarize what we found over here. We found an eigenvector, a single eigenvector, psi of x equals e to the minus, what is it, omega over 2 x squared that corresponds to an eigenvalue e equal to omega over 2. Let me go back and remind you why this happens to be the ground state of the oscillator. This happens to be the state of lowest energy. You won't get any lower energy than that.
A question? So going back to the classical Hamiltonian there, that you said it could be 0 because we would set p and x to 0 over there.
Yeah, for the classical, right.
So when you talk about the uncertainty principle, does that mean that there'll never be a zero energy state?
That's right. There will not be a zero energy state. There isn't. The lowest energy, this happens to be the lowest energy. There is no energy state lower than that. Okay, it happens to be the lowest.
So if you solve that equation with e equals 0, then...
Say it again?
So if you solve that equation with e equals 0, it would blow up?
If you try, that's right. If you try to solve it with e equals 0, you can try. You can just sit down and fiddle around with it.
Well, then you get eigenvector 1.
Eigenvector 1?
Psi is equal to 1.
No.
No?
No. Supposing you put in psi is equal to 1.
I'm just saying that's not square integral.
No, but that's not the problem. It also doesn't solve the equation. Put in psi equals 1. That would correspond to p equals 0. It doesn't correspond to x equals 0. Let's see. Yeah, good. All right, so good point. Let's put in psi equals 1. Why does he say psi equals 1? Psi equals 1 is a state of zero momentum. Okay? Zero momentum. It doesn't oscillate at all. Has no oscillations. All right, let's try it out. This would give 0, because after all, it's just p squared. And if the momentum is 0 for that wave function, it just gives 0. But this doesn't give 0. It gives x squared. And there's no way it can match against here. All right. If you try to solve this equation with 0 on the right, it doesn't solve for 0. It doesn't solve for anything. If you try to solve the equation with e equals 0, you can solve it. But it will simply blow up in both directions. It'll blow up in both directions, or at least one direction. Typically, it will blow up in both directions. You can force it by starting out the right way. You can force it to 0 in one direction, but it will blow up in the other direction. So E equals 0 is not a solution. But the other way to see it is just from the Schrodinger equation, from the uncertainty principle, that there can't be a state with both p and x equal to 0. It would violate the uncertainty principle.
Are you saying that you have two solutions because it's second order? You're saying no linear combination of those two solutions will ever give you, say for e equals 0, will ever give you a bounded...
Right. Right. That's correct. That's exactly right. Yeah, it'll either blow up. You can, by starting the initial conditions, tuning the initial conditions, you can make it go to 0 in one direction, but you'll find it blows up in the other. All right? Now, that's typically the case with any arbitrary value of the energy. It's a certain sign. Now, we found one value of the energy here. I knew the solution, so I plugged it in, but it is just a differential equation. You look at it long enough, and you see that e to the minus x squared will solve it. E to the minus omega over 2x squared will solve it, and that corresponds to an energy eigenvalue, which happens to be omega over 2. Possible to prove that this is the lowest energy eigenvalue. I won't try to do it right now.
You said that there's two solutions. What's the other solution?
Sorry?
What's the other solution?
Oh, it blows up like e to the plus x squared, or e to the omega over 2x squared. Yeah.
The same equation.
So usually we would get a family of solutions from this?
Yeah, you get a family of solutions which far away behave like a linear combination of e to the minus x squared. When I say e to the minus x squared, I'm ignoring the omega over 2.
No, I mean, once you have a particular solution, don't you usually get a family of solutions from that?
No. If you have two solutions for a linear equation, you can add them together with arbitrary coefficients and find a solution, find an arbitrary solution. Okay, so there are two linearly independent solutions. One looks like e to the minus omega over 2x squared. You can multiply it by any constant. And the other asymptotically looks like e to the plus omega over 2x squared. Yeah. In this particular case, the solution which goes to 0 in one direction also happens to go to 0 in the other direction. But that doesn't happen typically. The typical thing is you have two independent solutions, one of which goes to 0 in one direction and blows up in the other, and vice versa. And no combination will work in both directions.
Omega, you have to put as positive there in order for that to be.
Yeah, omega, sorry. Wait, say it again?
On the other side, E which omega has can never be negative.
Say it again.
Omega must be positive, therefore.
Yeah, I mean, right. In the original equation up there, it didn't matter whether omega was positive or negative because omega squared is positive. All right, so the correct statement is if you want the wave function to go to 0 far away, take the positive root. Right.
That proves that your eigenvector.
Yeah, that proves, that's right. Good. Okay, so the ground state energy of the harmonic oscillator is not 0, it is omega over 2. If I wanted to put back h bar, this is incidentally not dimensionally consistent. This is a frequency, which means a radian per second or an inverse time. This is an energy. If I want to get back to dimensionally consistent equations, I have to put h bar back in. Okay? So in particular, this means for any kind of reasonable frequency, and that can mean very, very high frequencies, enormously high, the energy will be very small because Planck's constant is very small. So the energy of the ground state is extremely small. And classically, where we ignore h bar, it's just equal to 0. That's the way things go, okay? Now, we want to see if we can find more eigenvalues. But before we do that, I think we will take a break so that I can have a little piece of cookie. All right, incidentally, this wave function is not normalized the way it is. I don't remember what the normalization factor is. Square root of omega and a square root of pi. You can figure it out. But there's some numerical coefficient that should go in front of it if you want it to be square integrated to 1. Okay. I put 0 here, size 0, in order to indicate not that it's 0 energy, but that it's the ground state. 0 indicates ground state here. This is the wave function associated with the ground state. All right, now, in order to figure out the rest of the energy levels, we use some tricks. And the tricks are specific to the harmonic oscillator, but they, well, let's put it this way, they're important. There's the tricks of constructing creation and annihilation operators. Operators which increase the energy and operators which decrease the energy. So let me show you how that works. Begin with the Hamiltonian in the form p squared over 2. Well, first of all, 1/2. Let's take the factor of 1/2 outside. 1/2 p squared plus omega squared x squared. Now, that's the classical Hamiltonian. It's also the quantum mechanical Hamiltonian. Let me do a manipulation which is fair and correct for classical physics, but which requires a little modification for quantum mechanics. So here's the manipulation. This is the sums of squares. So we can rewrite this as 1/2, the sums of squares. I'm just going to use a squared plus b squared is equal to a plus ib times, what is it, a squared plus b squared times a minus ib. Now, do I have that right? Yeah, I have that right. A squared minus times I is plus b squared, and the cross term cancels out. Okay, so let's write this in the form p plus I omega x times p minus I omega x. I haven't done anything. I've just rewritten the sums of squares in a different form. But now I'm going to give these guys names, p plus I omega x and p minus I omega x. They're essentially creation and annihilation operators. They're not quite, because I don't have the right coefficient in front of them, but we'll figure out what the right coefficient as we go along. The creation and annihilation operators, which we'll see what they do. We'll figure out what they do, what their definition is. But now, which one is which? Which one increases the energy and which one decreases the energy?
It's a trick question, so it's the minus increases.
Yeah, I think it's the minus. Yeah, maybe. Yeah, I know, but I'm not sure. Let's assume. All right. So let's call this one, and if it doesn't work, we'll figure out, we'll just interchange it. Let's call this one B plus. That's terrible, calling a thing with a minus sign B plus. I'm going to call it B minus, and the chances are we're going to regret it. Let's call it B minus, just because it has the minus sign in here. All right? And let's call this one B plus. Okay. Now, strictly speaking, in quantum mechanics, B plus times B minus is not equal to p squared plus omega squared x squared. And the reason has to do with the non-commutation of x and p. So let's see, if we wrote the Hamiltonian like this, if we tried to write that, let's forget this for a minute. Oh, I know where the factors go, but let's look at it. All right. If I tried to write the Hamiltonian like this, let's work it out. This would give me, first of all, p squared. It would give me 1/2 p squared. P times p is p squared. It would give me plus omega squared x squared when I multiply this out, plus omega squared x squared. That's good. Yeah, that's right. It's the xp and the px ones which are a little bit problematic. So from then it would give me plus I omega. And then we would have xp from here, let's put a bracket around it, xp from here minus px from the other one. Now I'm keeping careful track of the order of things. We have x to the left here, p to the right here, so that's xp, and here we have p on the left, x on the right. They come in with opposite signs. Classically, this would just go away. But quantum mechanically, the commutator of x and p is not equal to 0. What was the commutator of x and p? I h bar, right? So since we set h bar equal to 0, no, we've set h bar equal to 1, we can just say that the commutator here is I. I times I here is minus 1, so it looks to me like this whole thing here is 1/2 p squared plus x squared plus omega squared x squared plus or minus? Minus omega, right? Just minus omega? Minus omega. Minus omega over 2. I've taken into account the factor of 1/2 here. So the right thing to write then, this here is not p squared plus omega squared x squared. It differs from p squared plus omega squared x squared by omega over 2. All right, so if I really want to write this quantum mechanically, I think I have to add, yes, I have to add plus omega over 2, right? Did I do it right? Okay. All right, but this is just a constant. This is just a constant. it adds into every eigenvalue omega over 2, but if we can find the eigenvalues of p plus I omega times p minus I omega, that's good enough because we just add to every eigenvalue omega over 2. In other words, this here is just a number. It's not an interesting operator. If you take any operator and add an ordinary number to it, it just shifts all the eigenvalues by a common amount. It shifts all the eigenvalues by the same amount. Now, what is this? This is just the 0-point energy. This is the 0-point energy, the same thing that we found over here, omega over 2. So we've written the Hamiltonian in the form of a ground state energy plus something else. It had better be that that this thing, when it applies to the ground state, gives 0, right? Because we've already got the ground state energy here explicitly. So let's check that. Let's first check that this object, as it stands here, that this piece has eigenvalue 0 when it's applied to the ground state wave function. Let's do that exercise first. Okay, here we are. Here's our Hamiltonian. Let me rewrite it. Put it up here. H equals to 1/2 p plus I omega x times p minus I omega x. Notice these are Hermitian conjugates of each other. P plus I omega x is the Hermitian conjugate. Classically, it would just be complex conjugate. They're the Hermitian conjugates of each other. But good enough that, plus omega over 2. Plus omega over 2. Okay, that's our starting point. Okay, let's apply p minus I omega x to the wave function, and then multiply it by p plus I omega x and try to check whether we get 0. As I said, we should get 0 because we already have the ground state energy here. Okay, so p minus I omega x. What is p? P is minus I d by dx minus I omega x multiplied by e to the minus omega over 2x squared. Multiplied simply means you do the operations. Okay. Yeah, that looks right. Yeah, good. Okay. Now let's take out the factor of minus I. Minus I. And was this plus? I think it was plus then, right? Yeah. Minus I d by dx minus I omega x, both of them have the same sign, minus I in front of them. Okay, what happens when we differentiate once e to the minus omega over 2x squared? Let's see, can I remember? Yeah. It just gives us minus omega x e to the minus omega over 2x squared, right? No. Yes? No. No. Differentiating the x squared gives me a 2, and that eats this 2 here. Right? Okay. No, no 2. All right, so the first term just gives me minus omega x e to the minus omega over 2x squared, and the second term just gives me plus the same thing. So I don't even have to worry about the second factor here. The first factor, when it hits the wave function, already gives me 0. Okay? So that guarantees that when the product of these hits the wave function, we get 0, and this is the only thing left over. Good. So we've checked. Yeah, we're doing something right. This wave function satisfies the right property. Okay, these two seem to be interesting objects. In one, first of all, the Hamiltonian has been reduced to the form of something times its complex conjugate, or its Hermitian conjugate. Second, this object annihilates the ground state. The terminology is it annihilates the ground state. Let's explore these two objects a little bit more. Let's give them a name. I think I will call this one B minus, and this one B plus. Yeah, okay, so this one is B minus, and this one is B plus. First of all, B plus and B minus are Hermitian conjugates of each other, classically complex conjugates of each other. Okay, so that's an interesting fact. Next, they have some interesting commutation relations. Let's compute the commutator of B plus with B minus. Let's compute it and see what we get, just for fun. They're not observables, incidentally. Why aren't they observables? Because the individual ones are not Hermitian. They're not observables. They're not Hermitian. They don't have a complete set. In general, they don't have a complete set of eigenvectors. But nevertheless, let's figure out, we're going to do some algebra with them. It will be useful to know what the commutator is when we start multiplying them in various ways. It will be useful. OK, so what is this? This is a commutator of p plus I omega x with p minus I omega x. We start working out the commutator. The commutator of p with p is 0. The commutator, what about the commutator of I omega x with p? Well, commutator of x with p is I, right? So the commutator of these two, the commutator of these two here will give us I omega times another I. In other words, minus omega. The commutator of p with minus I omega x, well, the commutator of p with x is minus I. Commutator of x with p is I. Commutator of p with x is minus I. But there's another minus here. It just gives, the whole thing just gives 2 omega. 2 omega for the whole thing. So the commutator between b plus and b minus is just 2 omega. 2 omega. All right, it's perfectly OK to operate with b plus and b minus. It's a matter of definition and a matter of history and a matter of convention to divide b plus and b minus by the square root of 2 omega and call the result a. All right, so b divided by square root of 2 omega is called a plus, and b minus over square root of 2 omega is called a minus. And then what's the commutator of a plus with a minus? 1. All I did was divide this out so that the commutator would be 1. Now, as I said, this is somewhat a matter of convention. It is a matter of convention. It's a nice convention, we'll see, but nevertheless, it's just a convention to define a plus and a minus so that the commutator is 1. 1. All right, once we've done that, we can now rewrite the Hamiltonian in terms of a plus and a minus. In terms of the b's, let's rewrite this in terms of the b's. It's 1/2 b plus b minus. That's p plus I omega, p minus I omega x, b plus b minus, plus omega over 2. That's what it was here. But supposing I substitute in the a's, I'm going to have, instead of b plus b minus, I'm going to have a plus a minus times a factor of 2 omega. Okay, so this is going to just be just simple, so it's hardly even in the algebra. Just substitute, solve for the b's, square root of 2 omega, square root of 2 omega, a minus. All right, and now substitute for the b's in terms of the a's. And what do we get? I think we get omega a plus a minus plus omega over 2. There it is. Omega a plus a minus plus 1/2. So we've reduced the problem of the harmonic oscillator, the problem of finding the energy levels and the eigenvectors, but in particular the energy levels, to finding the eigenvalues of an operator A plus A minus, given that A plus and A minus have a commutator equal to 1. We now have basically an algebra problem, or a very, very simple operator problem. Let's condense it over on this side here. Here it is. Find the eigenvalues of A plus A minus. The half here just shifts all the eigenvalues. We don't care about that. At the end of the day, we'll add a half to all of them. We'll also multiply the result by omega. That's not interesting. Find the eigenvalues, e-values of A plus A minus, given that the commutator of A plus with A minus is equal to 1. Now, did I get the sign right? I wasn't very careful when I was doing it. Anybody having to go look quickly through the notes? It's either +1 or -1. I wasn't careful. I should have been more careful. Let's see.
Will these depend on which way x is?
Let me think. I think somewheres along here, I have a wrong sign, and it could be in any number of places.
I thought it was the -2 omega.
-2 omega?
No, I guess not.
I don't think so. It could easily be that I have a wrong definition, that this should be called A minus.
Somebody thought that. Somebody had proposed that.
Oh, well, that may be right. Yeah, that may be right. It may be that what I called A plus, I now regret and should call A minus. Of course, it is purely a convention, all right? But from memory, I remember that the commutator, let's see, of A plus with A minus should be, A plus, A minus, A minus, A plus, should be -1. Yeah. Okay, I think I have a definition wrong. The correct definition should be that this is called A minus. No. I think I have it right.
Why don't you just put it as -1?
Yeah, I think it should be -1. I don't know where I lost the sign. Let's just keep going. We'll find out if it should be -1 or +1. Commutator of A plus with A minus, I think, is -1. And that's just something I recall from having done this many, many times before.
Yeah,
Okay.
When you were computing the commutator, you said that the first term is supposed to be negative omega, and then you were subtracting another omega. So it should be -2 omega, which you then fold into the A, and you get -1.
Okay, good. Good. You say it should be -1.
Well, yeah, I think so.
Which is what happens if you define it as the other way around.
Let's not press our luck. Let's just say it's -1. With somebody having, and if it turns out wrong, we'll find out. Okay, that's our problem. A plus A minus equals -1. Good. Now, let me show you something. That if I take a eigenvector, let's call it O, this is supposed to represent the ground state. This is the ground state. What is the eigenvector of A plus A minus for the ground state? 1. Yeah, 0. Sorry, 0, 0, 0, 0. Remember, the ground state was A minus gave 0 when it hit the ground state. Okay. So A minus on the ground state is equal to 0. That was just this little calculation where we took P minus I omega x and multiplied it by e to the minus omega over 2x squared. We got 0. Okay. So A minus on the ground state is equal to 0. It's first fact. This now, incidentally, this does not represent the eigenvalue of the energy. Obviously it doesn't. The eigenvalue of the energy is omega over 2. It just represents ground state. The first state, we could have called it 1 for the first state, but we call it 0 for the ground state, for the ground state. Let's just call it ground state. Okay, A minus on this is equal to 0. What about A plus? Let's take A plus on 0. That's some new state. We can figure out exactly what its wave function is, and we will do it later. But let's see what its energy is. It may not be an eigenvector of energy. There's no guarantee that it's an eigenvector of energy, but it is. Let's just check it. How do we check that this is an eigenvector of the energy? All right. We simply, or an eigenvector, better yet, of A plus A minus. Well, we just multiply it by A plus A minus. Let's put a bracket around it. A plus A minus. If this object is an eigenvector of this operator, what does it mean? It means that this is equal to some number lambda times the original vector, which was A plus on O. In other words, I'm asking the question. Let's just take it as a question. Is this an eigenvector of the energy? And if so, what energy? Let's call, or what eigenvalue of A plus A minus? Let's call it lambda. I now take, not the commutator. This is not the commutator. It's just the product. I'm getting a little tired and I'm starting to make mistakes. A plus A minus hitting A plus on 0 may or may not give us some constant times A plus on 0. Is it clear why this is the eigenvalue condition for A plus 0, A plus on 0? If not, raise it right now and I assume that the lack of response means yes, that it's clear. Okay, now, here I have, if I now remove the bracket, I have A plus, A minus, A plus on 0. What I want to do is I want to interchange the order of these two. Let's interchange the order of these two, but I'm not allowed to do that. I'm not allowed to do it because they don't commute. But what I can do is I can say that A plus A minus minus A plus is equal to minus 1. And so the point is I can take A plus, here, let's rewrite it. A plus A minus plus 1 is equal to A minus A plus. All right, I have A minus A plus here. I can replace it by A plus A minus, but I have to add in a 1. So let's do that. This is equal to A plus, all right, times A plus A minus plus 1 on O. All I've done is use the commutation relation to invert the order of these two and then add in the extra 1 that's necessary there. Okay, now, A minus on 0 gives 0. So A minus on 0 gives 0. This can be ignored. And what do we get? We just get A plus on 0. This is a fairly long story, but what it said is that A plus A minus multiplying this vector here just gives 1 times the same vector. The conclusion, this new vector here is an eigenvector of A plus A minus with eigenvalue not equal to 0, but eigenvalue 1. Right? Let's go back to the Hamiltonian, to the energy. We have found a second eigenvector of the Hamiltonian. which is equal to A plus on O. We'll figure out what its wave function is in a moment, but the energy associated with it is omega. The energy is omega times 1 plus 1/2. 3/2. 3/2 omega. Where's the 3/2 come from? Well, we found out that this new state vector is an eigenvector of A plus A minus with eigenvalue 1, so I just plug in 1 for A plus A minus. In other words, by acting with the operator A plus on the ground state, we have added 1 unit of energy, measured in units of omega. We've added 1 unit of energy to the ground state. That's what we've done. Well, what happens if we do it again? Let's try to see what happens if we do it again. In fact, supposing we have an eigenvector of A plus A minus with eigenvalue n. In other words, supposing we have found a solution A plus A minus on some vector which I'll call n is equal to n times n. Now, you might get the idea that I'm thinking that n is an integer, and I am. But at the moment, I have no need to assume n is an integer. It's just a number. This is an eigenvector. Here is its eigenvalue by definition. May or may not be an integer. Supposing we have found one. Now, we found 2 such things. We found 2 already. We found one in which n is equal to 0, and we found one in which n is equal to 1. And they were related to each other by increasing n by applying A plus. This is very general. Let's see if we can see why. All right. Let's invent n plus 1. This is only its name. It doesn't really mean necessarily yet that it has eigenvalue n plus 1. It's just its name. And it's just gotten, by definition, A plus on n. Assumption, n is an eigenvector of A plus A minus with eigenvalue n. Right? Too many n's, but you get the idea. Let's see what A plus A minus does when it hits n plus 1. Let's see if this is really an eigenvector. Well, all we have to do is take A plus A minus A plus on n. Right? So far? Do I have it right?
Yeah, now we just do the same thing we did before.
Yeah. Okay. What, good. What do we do? We interchange the order of these two?
Right, we get the substitute A plus A minus plus 1 for A minus
Yeah,
A
we
plus.
get A plus A minus plus 1. Is that right?
Yeah.
And then the left-hand one goes away because A minus on n is.
A minus on
Oh,
n
no,
is
it's-
what? No. You see, yeah, A plus A minus on n. Yeah, A plus A minus on n is just equal to little n times n. So the whole thing is just equal to n plus 1, that's this, times n plus 1, times the eigenvector n plus 1. The eigenvector n plus 1 is just A plus times n. Get it? This is just n plus 1. That's what this says. And then A plus on n gives us the eigenvector n plus 1. Do the algebra. Do the algebra. All right, here's the upshot. Here's the theorem. That if you have an eigenvector with eigenvalue n of A plus A minus, and you hit that eigenvector with A plus to create a new eigenvector, a new vector, then that new vector is also an eigenvector of A plus A minus with eigenvalue n plus 1. This has eigenvalue n plus 1. I don't know how to write this. I'm getting tired and I'm losing it, but I think you get the idea. the creation operator, or this plus operator, A plus, acts on any eigenvector of A plus A minus to raise the eigenvalue by 1. Okay? Raises the eigenvalue by 1. The result is that the spectrum of eigenvalues starts at 1/2. The spectrum of eigenvalues of the energy starts at omega over 2, operating with A plus adds 1 unit, which means it becomes 3/2 omega. Hit it again, it becomes 5/2 omega, and so forth and so on. And the spectrum of energies is omega times n plus 1/2. Now, relative to the ground state, it's just omega n. So if we threw away the ground state energy, if we threw it away and say that's always there, then these raising operators simply add an integer multiple of omega, and strictly speaking, it's h bar omega. It's h bar omega energy each time it acts. Good. So here are all the eigenvectors of the energy. Start with O. What is O? O is the abstract vector associated with this. Multiply it by A plus. Multiply it twice by A plus. Multiply it any number of times by A plus. And what you make is the sequence of energy levels, omega over 2, omega 3 times omega over 2, 5 times omega over 2, and so forth. You know what I mean. Omega times 1/2, omega times 3/2, and so forth. Okay, so that is the complete solution of the harmonic oscillator. And it explains why the energy of oscillations is quantized. Quantized in units of the frequency times Planck's constant. Omega times h bar is the unit of energy. Each time you raise the energy level by A plus, you raise the energy by omega h bar. As I said, omega h bar is typically a very, very small energy. Okay, are there any questions now about the harmonic oscillator? Yeah?
Are there any other Hamiltonians that have equally spaced
No.
intervals?
No. Well, yes, I take that back. I take that back. There are other Hamiltonians which have equally spaced. There's one other one. It has not only positive energy levels, it has negative energy levels. It's just the angular momentum itself. Angular momentum comes in units of h bar omega. In units of h bar. And it can be plus or minus any integer. And if you took for the Hamiltonian the angular momentum itself, now why you would want to do that, what kind of system that would be a little strange system. Energy is equal to angular momentum. But it's a possible Hamiltonian. And yes, it would have equally spaced energy levels, but they would go from plus infinity all the way down to minus infinity. So this is the only one which has a spectrum which is bounded from below, which has a minimum energy level. If it has integer energy levels and a ground state, then it's a harmonic oscillator. Okay, so good. Any other questions? Yeah.
So question, so what physically this system would be? Would it be like maybe like an electron moving away from a charged plate or something like that? How would you've got to have something that restores the movement, right? A restoring force in it. Is that
What does a
the right way to
quantum
think
harmonic
about
oscillator
it?
look like?
Say it again?
What does a quantum harmonic oscillator look like?
What do you mean, what does it look like? It doesn't look like anything. You can't see it. I mean, quantum systems don't look like anything. I'm not sure what the question is.
But is it like an electron going around and acting, or I don't think?
No, the electron going around in an atom is not a harmonic oscillator. The reason, all right, when do you get harmonic oscillators? Or approximate harmonic oscillators? Go ahead.
Diatomic molecule.
Oh, a diatomic molecule is a very good example. Yeah. But there's a very general rule. If you have some potential energy for a problem which has a minimum, and it could be a function of any number of variables, but let's suppose it's a function only of one variable for simplicity, then if there's a stability point, the point at which there's stability, that means that the potential energy has some minimum someplace. So I don't care what the problem is. There's some problem in which there's a potential energy function and the potential energy has a minimum. Any function which has a typical function which has a minimum, near that minimum will look like a parabola. Unless, of course, you artificially tune the x squared term away. A typical situation, the general situation, except for some very special fine-tuned situations, is if you have a function with a minimum, that if you look nearby the minimum, it looks like a parabola. Right? A parabola means that nearby the minimum, if I study the system as in terms of deviations away from the minimum, let's call that variable x, deviation from the minimum, the potential energy will look like x squared. If there's a stable point, that means if you displace it a little bit, it will be pulled back to the origin. That's the assumption that there's a stable solution. So if there's any kind of stable solution, it will get pulled back to the origin. That's what stability means. If you pull it the other way, it'll get pulled back to the origin, and it becomes a harmonic oscillator. So all kinds of systems. So as was mentioned, if you have a diatomic molecule, just two atoms, and there's some stable configuration of the atom, of the molecule, then small deviations will oscillate about, but they'll quantum mechanically oscillate. I'm not sure what it means to ask what does a quantum mechanical system look like. If you try to find out what it looks like by hitting it with a photon, you disturb it. And it's not possible to really take a photograph of a quantum mechanical system without disturbing it. So it's a bad question. What does a quantum mechanical system look like? On the other hand, we can ask what the various energy levels, what the probability distribution for them looks like. All right? The ground state, the probability distribution is a Gaussian, a bell-shaped curve with a width which is controlled by omega. The bigger omega gets, the narrower the distribution. The distribution has a width which is controlled by omega. Why does the width get narrow with omega? Well, if you go back to the original definition of what omega is associated, the square of omega is the spring constant. All right? The tighter the spring constant, the more tightly the oscillator is held to the origin. All right? The more tightly it's held to the origin, the less spread the wave function will have. So that's the character of this. The bigger omega, the less the spread of the wave function. But apart from its spread, it's just given by a bell-shaped curve by a Gaussian function of x. Gaussian means e to the minus x squared. All right, let's go to the next energy level. Let's see if we can find out what the next energy level looks like. It's actually easy. All we have to do is say that the next energy level is given by A plus on O. Now, what was A plus? Do we have A plus written down someplace? I lost it. It was P plus I omega x or P minus I omega x? I'm not sure. Do we have it? No, it's gone.
Well, I think it should be P minus I omega x.
Oh, here it is. Here it is.
But
Here
you
it
don't
is.
speak plus.
Yeah, but that was the mistake that we made. That should be B plus, and that
No, I
should
think
be.
we said this was right. No, we said this was right.
You don't get the minus one.
Yeah, we do.
No, you don't, because when you did the commutator, you made a mistake. Let him go, Mike.
Yeah, why don't we just work it out this way, and if it comes out, the answer comes out bad, then you know.
Okay.
You want to do it over?
No, he wants you to go forward. Go forward, assuming just your way.
What's that?
Go forward,
on.
assuming P plus I omega.
I'm wrong?
No, move on.
Move on. Okay, move on.
Your way.
All right. There's an easy way to tell. If this is A minus, it should annihilate the ground state.
Which it does.
Which it does. So this is A minus.
Okay.
End of story. Yeah. Good. So this one must be A plus. Good. Or B plus. Doesn't matter. A plus or B plus. Okay. So let's then take the ground state, e to the minus omega over 2 x squared, and hit it with B plus. We should find the next energy level. Let's see what the wave function looks like. So B plus is 1/2, forget the 1/2, there's no 1/2. B plus is minus I d by dx plus I omega x. That's B plus, where I've used minus I d by dx for P. Now, hit that with e to the minus omega over 2 x squared. What do we get? Okay, as I remember, let's first of all take out the factor of I. Minus d by dx gives us what? Omega gives us a factor of minus omega x. Right. Both of these give us omega x. Both of them give us omega x. So apart from a factor of I, which we can put in, and a factor of 2, which we can put in, it's x with an omega, x e to the minus omega over 2x squared. The factor of 2 and I and omega, that's just a multiplicative constant. The wave function looks like the Gaussian multiplied by x. All right, that's a function which asymptotically still goes to 0 this way. E to the minus omega, omega over 2x squared goes to 0 much faster than x grows. So it still goes very quickly to 0, but now it has it looks like this. It has a 0 in the middle here. Let me make it more precise. Let me try to draw it better. It looks like this. It's 0 at x equals 0. It has one node. A node is just a place where it crosses the real axis, where it crosses the axis. So that's the wave function of the first excited state. It's 0 at the origin, and far away it looks pretty much like a Gaussian.
Is it upside down?
What the? Well, is it upside down?
Yeah,
Yeah. Multiply it by minus. In fact, it's not just upside down. It has a factor of I missing and omega.
okay.
Yeah. Just throw this away. It's a constant and put a minus in. And that's it. Good. Okay. Each time, you try this out. Go to the next one. Go to the next one, you just take, what do? You take this one, which is x e to the minus omega over 2x squared, and you do it again. Minus I d by dx plus omega x. All right. The omega x is going to give you an x squared. That's pretty clear. The minus I d by dx is going to give you two terms. One of them will come from hitting here. It'll give you another omega x. And the other one will hit this. It's quite clear what you're going to get is a polynomial, a quadratic polynomial. All right. All right. Each time you hit it, you create another 0. The next one would look something like this. 2 zeros. And would be the Gaussian times a polynomial with, sorry, like this. Would have 2 zeros. Each time you raise, you add one more 0. You go from, this is an antisymmetric wave function. Antisymmetric means the opposite sign on the two sides. You go back and forth from symmetric to antisymmetric to symmetric to antisymmetric, and you add one more 0. So what happens, is you start to get things which oscillate more and more rapidly. That corresponds to putting in more momentum. Rapidly oscillating wave functions indicate momentum. Well, that's not surprising. You hit the oscillator and you excite it to a high level of excitation, it's going to be whizzing back and forth. The whizzing back and forth means that there's going to be short wavelengths in the problem. The harder you hit it, the more there's going to be large momentum in the wave function. What's more, it's going to sort of spread out. It's always going to be asymptotically small, but it will spread out and do things like this. So what this corresponds to is when you hit it hard, you spread the wave function out over a bigger distance, corresponding to the fact that it swings way out and swings way out in the opposite direction, and you give it a lot of oscillation, indicating that you've given it a lot of momentum. So it's kind of fun to work out the first 5 or 6 wave functions and see how they look. They start to look more and more like this. And that's the harmonic oscillator. The main thing is that the energy levels are quantized and that you go from energy level to energy level by these operations here, the A+ operation. Incidentally, as you might expect, if you take a wave function with a given energy and you apply the lowering operator, the A-, as you might expect, that lowers the energy down 1 unit until you get down to the ground state. When you get down to the ground state, A- gives you 0. Nothing left there. So that's the character of the harmonic oscillator. We did not get to angular momentum. At some point in this course of lectures, when we get to quantum field theory, I will discuss angular momentum for you. So that's the harmonic oscillator. Any questions? Yeah.
Are the zeros the polynomials for real values?
What's that? Say it again. Ask again.
I was asking.
Who's asking?
I was asking.
Oh, up there. Okay, yeah.
Are the zeros the polynomials for real values?
Real values of x. Yes, yes. Is it obvious? Not completely. No, I don't. It's not obviously obvious, but it is obvious. No, it's not obvious to me right now. Right. Yeah. I think it wouldn't be too hard to demonstrate, but at the moment I'm tired and it's not obvious to me, no. But it's true.
So above the ground state, there are some values of x for which the probability is 0. There are some values that cannot.
Yeah, that's right. There's points where the probability is 0. Right. If you look for the particle there, you won't find it. Right. Weird, huh? Nevertheless, the particle goes swinging back and forth in some harmonic oscillator sense. Right. Destructive interference at those points.
Now, a question, is there any meaning in asking why do we have quantized states, or is it just accepting?
Why do we have quantized
energy, basically?
I just showed you.
Yeah, I know, but okay, but it seems to me that the mathematics is fitting something. No, it doesn't. This isn't the kind of the cause of this. You know what I'm saying?
I'm afraid it is the cause.
Oh, well,
don't have
I
quantized
suppose what he
states.
wants is some physical justification for square integrability or something.
You don't always have
So
quantized states, do you? You can have a continuous set of eigenvalues, like on your 3 particle.
Only, typically you don't get a continuous set if the particle is confined in some potential that keeps it yeah, there are times when you get continuous energy levels, and basically it's when the particle is free to move off asymptotically without being... See, the harmonic oscillator, the particle, no matter how much energy you give it, is never free to asymptotically fly away from the system. It's always pulled back. The wave functions are concentrated. When the wave functions are concentrated, you are going to get discrete energy levels, always.
If you have a escape velocity, greater than escape velocity, then you have continuous.
That's essentially right, yeah. When the momentum, or when the energy is above the escape energy, let's call it, When the energy is above the escape energy, then you have continuous energy levels. Right.
I suppose the question he was asking is why are the functions the solutions that blow up excludable? Why can't they happen?
Well, in that case, the particle has all of its probability infinitely far away. In other words, if you normalize the wave function, then all the probability is infinitely far away. The probability of finding it in any finite place is 0. So, okay, perfectly good. Nothing wrong with it, except you'll never find the particle, so let's throw it away.
Exactly. Okay.
Yeah. Yeah. It also has infinite energy because the potential energy will be infinite, since it's right. No, I probably never spelled it out, but strictly speaking, the state vectors of a properly defined quantum mechanical system have to be normalizable. That means that the integral of psi star psi or the sum or whatever it is, should be able to add up to 1. A probability
in some
distribution.
Sense, what you've just said, though, is more satisfying than the other way is to just make that be an axiom.
Yeah, you can make it be an axiom, and it's a true axiom, it's a good axiom, but if you ask why do you make that axiom, well, it forbids these systems where the particle has 0 probability of being found anywhere in the finite region of space. Yeah, that's right. Okay. All right, next time we will go on to field theory. I can take I don't have to write new notes for next time. Yeah.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.